Hey everyone, welcome to another episode in Physics is Fun. Today is going to be about covering a 2D kinematics problem. Let's jump into reading the question. An Apple iPhone is thrown horizontally off a cliff with a speed of velocity initial equals 18.0 meters per second. The cliff is h equals 50.0 meters above a body of water. A. What are the coordinates of the phone's initial position? B. What are the components of the initial velocity? C. Describe the vertical and horizontal motion. D. Write the equations for the x and y components of the velocity of the phone as a function of time. E. Write the equations for the position of the phone as a function of time. F. When does the phone impact the water? And lastly, G. What speed and angle does the phone have on impact? Let's start with solving for A to C. For part A, the coordinates for the initial position are x equals 0 meters and y equals 0 meters, or coordinate notation 0 meters, 0 meters. Part B, the components for the initial velocity are velocity initial x, given equals 18.0 meters per second, and the velocity initial y starts from rest, so is 0 meters per second. Part C, the velocity initial x is a constant at 18.0 meters per second, and velocity initial y is 0 meters per second, and in free fall accelerates at negative 9.8 meters per second squared. These were simple enough, so let's move on to the rest, which are much more complex. For part D, we need to find the components for velocity as a function of time. The equation needed for velocity as a function of time is the velocity final equals velocity initial plus acceleration times time final minus time initial. We have the relation between velocity and time. With the equation, it's time to calculate. Rewriting the equation for our x component velocity, final x equals velocity initial x plus acceleration of x times time final minus time initial. The x velocity is constant, so there is no acceleration, and it all goes to 0, so we can cross it out. We get velocity final x equals velocity initial x, which makes sense since it's constant. The y component velocity final y equals velocity initial y plus acceleration of y times time final minus time initial. The velocity initial y is just 0, and time initial is 0, so we can cross them out. This leaves velocity final y equals acceleration times time final, or velocity final y equals negative g times time final. We have got the x and y components and can now solve for E. Part E, to find the position of the phone as a function of time, we need the position and time, so the equation x final equals x initial plus velocity initial times time final minus time initial plus 1/2 times acceleration times time final minus time initial squared. With the equation, we can plug the variables in, so now let's calculate. Rewrite the x final equals x initial plus velocity initial of x times time final minus time initial plus 1/2 times acceleration times time final minus time initial squared. And we are solving for x final. X initial, acceleration in x direction, and time initial are all 0, so we can cross them out and get the equation x final equals velocity initial of x times time final. To solve for y now, y final equals y initial plus velocity initial of y times time final minus time initial plus 1/2 times acceleration times time final minus time initial squared. Y initial, velocity initial in y direction, and time initial are all 0, so we can cross those out. This leaves the equation y final equals 1/2 times acceleration times time final squared, or y final equals negative 1/2 times g times time final squared. With the equations for x and y position, let's move on to solve F. To find when the phone impacts the water, we need the time, and we do not have the velocity final for y, So we must use the x final equals x initial plus velocity initial times time final minus time initial plus 1/2 times acceleration times time final minus time initial squared. With the equation, we can plug in with the y variables, so let's calculate. Y final equals y initial plus velocity initial of y times time final minus time initial plus 1/2 times acceleration times time final minus time initial squared. The y initial, velocity initial in y direction, and time initial are all 0, so we can cross those out. Y final equals 1/2 times acceleration times time final squared, the same one as part E. Let's solve for time final now. Divide both sides by 1/2 times acceleration and cross out on the right to get 2 times y final divided by acceleration equals time final squared. To find time final, square root both sides to get time final equals square root of 2 times y final divided by acceleration. Plugging in numbers to get square root of 2 times negative 50 meters divided by negative 9.8 meters per second squared. Negatives become positive and the meters cancel, and bring the seconds squared up to get a final answer of 3.19 seconds. With the phone impacting the water in 3.19 seconds, let's solve for the last part, g. To find the speed and angle of the phone, we need vector components at our final time. Remembering from part D, we solved the final velocity components, so rewrite those. Velocity final of x equals velocity initial of x, and velocity final of y equals negative g times time final. We have what we need, so let's calculate. Velocity for x is given, so to solve for velocity of y, plug in to get velocity final of y equals negative 9.8 meters per second squared times 3.19 seconds. Cross these seconds to get a velocity final of y equals negative 31.26. I forgot my negative sign here. Now to solve for the final speed or magnitude of the vector, we use the resultant vector equals the square root of velocity final of x squared plus velocity final of y squared. Plug in and get square root of 18.0 meters per second squared plus 31.26 meters per second squared, and calculate it out to get 36.0719 meters per second. Now we have the magnitude and need the angle. So to find the angle, we use tan of theta equals the y component over x component. To get the angle, we find the inverse tan of this y over x, and so plugging in tan inverse of negative 31.26 meters per second divided by 18.0 meters per second equals theta at the angle of negative 60.06 degrees. So we have found the final velocity to be 36.07 meters per second at negative 60.06 degrees. There were quite a lot of parts to this, but after solving for a to d, we used those to find our x and y components to figure out the phone hits the water at 36.07 meters per second at negative 60.06 degrees. I hope these intro problems are as helpful for you as they are for me. Thanks so much for watching. Hope you come back to learn more exciting material, and see you next time.